Welcome dear learners. We are continuing the course Quantum Chemistry. In the present module, we are discussing operators in quantum mechanics. The contents of this module are operator, definition of operator, linear and nonlinear operators, Laplacian or Laplace's operator, commuting and non-commuting operators, the commutator and non-commuting property with Heisenberg uncertainty principle. First of all, an operator. What is an operator? The definition is like this. An operator is defined as a shorthand representation of well-defined mathematical procedures to be performed in an arbitrary operand. That means it is a shorthand representation. An operator is a shorthand representation of which mathematical procedures to be performed in an operand. This is a simple example for an operator. Here the operator is d by dx or the differential operator, and d by dx of sin x, you know the result is equal to cos x. In this case, sin x is the operand. You can replace it with the cos x or e raised to x, any mathematical function, that is known as the operand. And the operation of d by dx on sin x leads it to the result that is cos x. Hence, d by dx is called the differential operator. As I already mentioned, sin x is the operand. Therefore, an operator is a shorthand representation of the mathematical procedures to be performed in an operand. By seeing this d by dx, it gives an information that we are going to differentiate the operand with respect to x once. That is the indication, that is the information we obtained from this shorthand representation d by dx. Now, there are so many examples for operators. See, for example, I am multiplying with a constant k. See, the function is f of x. K into f of x. Here k can be considered as an operator. K can be considered as an operator. Another operator is d square by dx square of cos x. See, cos x is the operand. I am going to differentiate cos x with respect to x twice. That is the indication I got from this operator d square by dx square. Now, dou by dou x of cos x y. If more than one variable is present, sometimes we adopt partial differentiation. Dou by dou x simply means we are differentiating the function, the operand cos xy with respect to x only. That means keeping y as a constant. So, dou by dou x is the partial differential operator. In quantum mechanics, we are dealing with the several kind of operators. Then, multiplying with the k is called a constant operation. In certain cases, we have to multiply a mathematical function or an operand with the 0. That is, one multiplication with the 0 into an operand f of x, the result will be 0. This is called annihilation. Here, 0 is termed as 0 hat, or we can call it as the null operator. It should be noted that in order to distinguish an operator must always use this notation cap. So, a cap or a hat indicate that it is an operator. So, in order to differentiate a function or a quantity from an operator, we place a hat or a cap on the operator as a notation. Now, in quantum mechanics, there is a very important operator called total energy operator, that is called Hamiltonian operator. The Hamiltonian operator is denoted as H hat. In quantum mechanics, there are other operators known as position operator, momentum operator, etc. The momentum operator Px hat, that is mathematically minus IH cross dou by dou x. We can familiarize different type of operators in coming slides. Now, in quantum mechanics, operators are mathematical objects that corresponds to physical quantities such as energy, momentum or position. This implies that in quantum mechanics, the physical quantity can be represented by using operators. Energy can be represented by energy operators, time by time operator, position by position operator, momentum by different momentum operators and its components, also angular momentum by angular momentum and its component operators. So for every physical quantity, there can be some operators. Operators act on wave functions. In quantum mechanics, we are using operators to operate on wave functions, which represent the state of a quantum mechanical system. This operation produce new wave functions that represent the state of the system after physical operation. Now, two important kind of operators in quantum mechanics. They are linear operator and non-linear operator. We can differentiate a linear operator and a non-linear operator by checking a mathematical condition. Let A hat is an operator. I am taking two arbitrary mathematical functions, namely f of x and g of x. So, f of x and g of x are two arbitrary mathematical functions and A hat is an operator. A hat can be considered as a linear operator if it satisfies a new condition. The condition is A hat of f of x plus g of x equal to A hat f of x plus A hat g of x. If this mathematical condition is satisfied, we can call A hat as a linear operator. So, an operator A hat is said to be linear if A hat of f of x plus g of x equal to A hat f of x plus A hat g of x. If this equality is not valid, that means LHS not equal to RHS, we can call it as a non-linear operator. Now we can take some example for linear and non-linear operator. First of all, we can take the differential operator, that is d by dx. We can check whether it is a linear operator or a non-linear operator. And now I am taking two functions, f of x, let f of x equal to x square and g of x equal to sin x, and g of x equal to sin x. Then d by dx of f of x plus g of x, that is d by dx of x square plus sin x. It is very well clear that the result is d by dx of x square plus d by dx of sin x. That means the operator d by dx satisfies condition for linearity. That means A hat of f of x plus g of x equal to A hat f of x plus A hat g of x. So, the differential operator d by dx is a linear operator. Now, I am taking the operation of taking square. Taking square. Taking square is also a mathematical operation. That is, The two functions are f of x and g of x. I am taking the square, and here in this case, f of x square plus g of x square plus 2f of x g of x is the result. This is the result of taking square operation. And from this it is clear that f of x plus g of x square not equal to f of x square plus g of x square. That means the above condition. That is a hat of f of x plus a hat of f of x plus g of x equal to a hat f of x plus a hat g of x is not valid whenever I am taking the square. That is, taking square operation is not a linear operation. In a similar way, taking square root is also a non-linear operation. That means f of x plus g of x, the whole raised to 1 by 2 not equal to f of x raised to 1 by 2 plus g of x raised to 1 by 2. Hence, taking square root, taking square, taking nth power, taking 1 by nth power, etc. are all non-linear operators. Now, what about multiplying with a constant? That is, the constant is k into f of x plus g of x. Absolutely no doubt. The result is kf of x plus kg of x. That is, multiplying with the constant or constant operation is a linear operation. By this, we familiarized different kind of linear and non-linear operators. This is the equation to be checked for linearity and non-linearity. That is, a hat of f of x plus a g of x equal to a hat f of x plus a hat g of x. If it is valid, the operator is linear, otherwise non-linear. Now, we can move on to another important operator in quantum mechanics. That is called Laplacian operator or Laplace's operator. The Laplace's operator was first applied to the study of celestial mechanics or the motion of objects in outer space by mathematician Pierre Simon de Laplace, and the operator we are going to study is named as Laplacian operator or Laplace's operator. The Laplace's operator is represented as del square. Del square. Here del is otherwise named as nabla. The Laplace's operator is del square, and this is mathematically dou square by dou x square plus dou square by dou y square plus dou square by dou z square. This operator is very significant as far as the Schrodinger wave equation is concerned. This del square is known as the Laplacian operator or Laplace's operator, which is a differential operator, second order differential operator, and differentiation is performing partially twice with respect to each variable concerned, namely x, y and z. Del square equal to dou square by dou x square plus dou square by dou y square plus dou square by dou z square. This is the Laplacian operator. Del square is Laplacian operator. Del is called the nabla, N-A-B-L-A, nabla. Yeah, that about the Laplacian operator. Now, commuting and non-commuting operators. This is an important area in quantum mechanics as far as operators are concerned. We can classify operators, two operators, as commuting or non-commuting based on some mathematical features. To identify the concept of commuting and non-commuting operators, we have to first select two arbitrary operators. And for this discussion, I am selecting the arbitrary operators as A hat and other one is B hat. Also, I am taking a function or an operand f of x. The two operators A hat and B hat are said to be commuting to each other, are commuting operators if A hat B hat f of x equal to B hat A hat f of x. What is the meaning of this mathematical expression? Here, f of x is the operand. In f of x, first B hat is operated. On that result obtained after operation of B hat, we perform one more operation by A hat. So, here B hat operate first, followed by A hat. That result must be same as if A hat operate first, followed by B hat. Then, LHS and RHS are equal. We can say that A hat and B hat will commute each other. That means two operators said to be commuting each other if and only if the order in which they perform in an operand will commute. That is, the order should commute. First A, then B, or first B, then A. Both give same result. Then A hat and B hat said to be commuting each other. If this is not valid, A hat and B hat are said to be the non-commuting operators. So, there are commuting operators and there are non-commuting operators. See, for example, d by dx and constant operator are excellent example for commuting operators. Let us check it. For example, I am taking a function. F of x is the function. I operate first with k, then with d by dx. What is the result? The result equal to k into d by dx of f of x. d by dx of f of x can be marked as f dash x. Then I am taking the opposite order, that is f of x. First I differentiate with respect to x, then I multiply with k. The result is also k into f dash x. That is d by dx hat k hat f of x equal to k hat d by dx hat f of x. I am using hat to distinguish the operators. This result is valid and we can say that the operator k hat, that is constant operator, and the differential operator are mutually commuting. If two operators are not satisfying this result, they are said to be non-commuting operators. One excellent example for non-commuting operator is the position and momentum operator. Position operator marked by x hat and momentum operator marked by px hat. These two operators will not commute each other. The details of which can be studied in the coming slides. That about the commuting and non-commuting operators. Now, we are introducing a new parameter, a new combination operator called commutator. The aim of this commutator operator is to check whether two operators commute or not. That is done by the commutator operator. By definition, the commutator of two operators, let A hat and B hat are two operators, their commutator can be marked like this, square bracket A hat B hat. This should be read as commutator. Commutator of A hat and B hat. and this is theoretically equal to A hat B hat minus B hat A hat. So the commutator A hat to B hat is equal to A hat to B hat minus B hat A hat. If A hat and B hat commute each other, their commutator, that is A hat to B hat, commutator of A hat to B hat, should be equal to 0. If the result is not equal to 0, we can say that A hat and B hat are non-commuting operators. So what is a commutator? A commutator is a combination operator represented as square bracket inside which A hat to B hat. That is equal to, commutator equal to A hat to B hat minus B hat A hat. If the result of this combined operator is equal to 0, we can say that a commutator is equal to 0. If commutator is 0, the operators will commute each other. If commutator is a non-zero quantity, the operators will not commute each other. That about the commutator operator. We can take some examples to find out the commutator and to assess the commuting property of concerned operators. First of all, commutators have some interesting relations also. First of all, we are doing a mathematical proof, that is, we have to prove commutator A hat to B hat should be equal to minus of commutator B hat A hat. We can prove it, and there are some steps to show LHS equal to RHS. By definition, the commutator of A hat B hat is represented as A hat B hat minus B hat A hat minus B hat A hat. Or I am marking it as, I am taking a negative sign outside, minus of B hat A hat minus A hat B hat. Now, what will be B hat A hat commutator? B hat A hat will be equal to B hat A hat minus A hat B hat. So, this result is equal to commutator of B hat A hat. Therefore, minus of commutator B hat A hat. Hence, we can say that commutator A hat to B hat is equal to minus of commutator B hat A hat. That means, inside the commutator, if we exchange the position of the operators, there will be occur a negative sign. This about the proof. Now, evaluate the commutator K1 by X. Inside this commutator, there are two operators. One is the constant operator, other one is reciprocal of position operator, that is 1 by X operator. We have to evaluate the commutator K into 1 by X. After the evaluation, we are able to predict whether K and 1 by X commute or not. How we can predict the commuting property? If the commutator evaluated is equal to 0, we can say that K and 1 by X commute each other. If not equal to 0, they are non-commuting. That we are going to check whether they commute or not by evaluating the commutator. There is a procedure for the evaluation of the commutator, and the procedure is like this. By definition, commutator of A hat to B hat is equal to A hat to B hat minus B hat A hat. In analogy with this, by taking K and 1 by X, I can write this expression K into 1 by X minus 1 by X into K. All these are operators. In order for an operator to be valid, there must be an operand. For the sake of convenience, I am introducing an arbitrary operand f of x. I am selecting f of x because here x is the variable. If y is here, I can take f of y as the variable. If x and y are here, I can take f of x, y as the operand. So for the present problem, I select an arbitrary operand f of x and I mark this as equation number 1. I am putting f of x on left hand side and right hand side of this equation number 1. Therefore, commutator k 1 by x f of x equal to f of x into this quantity. That is, each quantity should be multiplied with f of x. That is k into 1 by x f of x minus 1 by x k into f of x. It is clear that k into 1 by x f of x same as, that means k into 1 by x f of x is same as 1 by x into k into f of x. That is, I can put like this, f of x can be taken as outside, f of x into k by x minus k by x. That is, f of x into k by x minus k by x is 0. I have to remove, this is equal to k into 1 by x f of x. That is equal to f of x into 0. I have to remove f of x from both the sides, because for the sake of doing calculation only I am putting f of x in the first step. So I have to remove f of x in the final step. After removing f of x in the final step, I got the result, the commutator k 1 by x equal to f of x into 0. That is, k 1 by x is equal to 0. This means that the commutator k into 1 by x equal to 0, which means the operators k and 1 by x are commuting operators. Now, another commutator to be evaluated is x into d by dx. We can proceed in the same fashion. We know the commutator a hat to b hat is equal to a hat to b hat to minus b hat a hat. Here a is x and b hat is d by dx. Proceeding in the similar way, commutator x d by dx equal to x into d by dx minus d by dx into x. For a function to be valid, I have to put for this operator to be valid, I have to put a function, namely f of x, on both the sides. Therefore, x d by dx of f into f of x equal to x into x into d by dx f of x minus d by dx into x into f of x. So, the first term, that is x into d by dx of f of x, I can mark it as f dash x minus d by dx into x into f of x. Here we have to apply the product rule of differentiation. That is, applying this x f dash x minus first function, that is x, into differential of the second, that is f dash x. Minus is carrying on, minus second function, that is f of x, into differential of the first, that is dx by dx. Dx by dx is equal to 1. So, the first two term will vanish out and the result is minus f of x. That means minus 1 into f of x is the result. I put f of x for doing the calculation. So, in the final step, I have to remove f of x from both the sides. So, f of x is replaced from both the sides. Therefore, I got the commutator x d by dx equal to RHS, that is equal to minus 1. Hence, the two operators x and d by dx have a commutator which is a non-zero value. That means commutator not equal to 0. That means the operators x and d by dx are non-commuting operators. We can move on to another important example, that is the commuting property of position operator and momentum operator. This is very important in quantum mechanics since it has a firm connection with the Heisenberg uncertainty principle. Then what is the position operator? If the body is moving along x-axis, the position operator can be marked as x hat and the momentum operator can be marked as px hat. The body is moving along x direction. So we have to evaluate the commutator x hat, px hat. And by definition it is equal to x px minus px x. You can put hat also, and px hat is equal to minus I h cross dou by dou x, minus I h cross dou by dou x. These details we can study with the operator postulate of quantum mechanics. Now simply keep in mind px hat or momentum along x direction operator is minus I h cross dou by dou x, where s cross is a constant, h by 2 pi is s cross. This is otherwise called Dirac, D-E-R-A-C, Dirac, named after the physicist P.A.M. Dirac. So px hat is equal to minus I s cross dou by dou x. I can substitute here also, then introduce a new function, that is new operand f of x, and proceed in the same way as we have done in the previous problem to get the value of the commutator, and we can proceed like this. Now I am putting an operand f of x on LHS and RHS, therefore x hat px hat f of x equal to x hat px hat f of x minus px hat x hat f of x. X hat simply means multiply with x. Px hat is minus I h cross dou by dou x. Substitute the values here and we can proceed accordingly. X into, what is px hat? Px hat is minus I h cross dou by dou x. Since we are having only one variable, dou can be replaced with the d. That is no need for the partial differentiation. We can use complete differentiation. Therefore, x into minus I h cross d by dx is okay. D by dx of f of x minus I h cross d by dx of x into f of x. From these two sides, I can take minus I h cross as constant outside. So this into x into d by dx of f of x, that you know it is equal to f dash x. Minus I h cross took outside. So here there is a remaining minus term. Minus d by dx of x into f of x. Here also you have to use the product rule of differentiation. That is minus I h cross x f dash x minus first function to differential of the second. X f dash x. Minus is carrying on, minus f of x, minus f of x. X f dash x, f dash x vanishes, and the result is equal to minus I h cross into minus f dash x. That is equal to I h cross f of x. I have to replace f of x from both the sides. So the result of the commutator x px commutator or x hat px hat is equal to, the result is equal to I h cross. This simply indicates that the two operators, position and momentum operator, are not commuting each other. Now another problem, we have to prove x raised to n px hat is equal to I h cross n into x raised to n minus 1, where n is any positive integer. This is an analogous problem as we have done in the previous case. Therefore, I am moving to the solution directly. That is, the commutator x raised to n hat px hat equal to x raised to n px minus px x raised to n, where n is any positive integer. I am putting f of x on both the sides and proceeding in the similar way. X raised to n px f of x equal to, you know, px is minus ih cross d by dx. That can be taken outside the sign also. Minus ih cross into x raised to n px, that is d by dx f of x, minus another term d by dx of x raised to n into f of x into f of x. That is minus ih cross into x raised to n f dash x minus first function x raised to n into f dash x minus f of x into differential of the second. What is differential of x raised to 1? X raised to n, that is n into x raised to n minus 1. On simplifying, these two terms vanishes, minus minus goes to be plus. So the result is ih cross n into x raised to n minus 1 multiplied with the f of x. I have to remove f of x from both the sides. So I got the final result of the commutator x raised to n px equal to ih cross n into x raised to n minus 1. This is the result. Ih cross n into x raised to n minus 1. That all about the discussion about commutator and commuting property of operators. Now, non-commuting property and uncertainty principle. I already mentioned that the position operator and the momentum operator are two non-commuting operators. The non-commuting property of operators representing physical quantities can lead to uncertainty principle. We are familiarized about uncertainty principle. It is impossible to determine the position and the momentum of a moving subatomic particle simultaneously and precisely. That is a statement of the uncertainty principle. If two operators will not commute each other, the properties represented by them cannot be determined simultaneously and precisely. For instance, the position and the momentum operators will not commute each other. This leads to the Heisenberg uncertainty principle. That all about the present discussion. Thank you.